SwayamPrabha. Digital India. Educated India.
Yeah. So this is a form of the equation. Now, in addition, we'll have this here b times q dot term. Okay. Okay. So this is a form of equation that you'll have. Okay. So plus bq dot. Okay. So we are ignoring gravity in this case. Okay. So I'm now, like, not representing the dependence on q and q and q dot of c and d. So this is our equation. If you recall, the controller tau is having this form dA plus now I'll combine this b plus c together here times nu, okay, minus kd into r. Okay, so if you now see, this a is given as nu dot, okay, and this nu is given as qd minus lambda e. Okay, so remember, these are all vectors here, and this is matrix here. Okay, typically a diagonal matrix and positive definite matrix. So A will be equal to qd double dot minus lambda e dot. Okay. So we will use this form. Okay, this A and this while substituting. Okay. So here, if you come now, like your b q. Okay, so let's start with d only here. Okay, so that we are consistent now with the, so this d q dot q double dot plus, now again we combine here this b plus c terms, q dot is equal to, now if I substitute this here, d times a is q d double dot, okay, minus lambda e dot plus now b plus c qd minus, this should be qd dot, should be dot here, okay, minus lambda e minus kd times r. Okay, so if I bring these terms on the other side, now this becomes now dq double dot minus qd double dot plus lambda e dot. Now this b plus c, where I can take out, and q dot minus qd dot plus lambda e, and then this kd times r is equal to 0. Okay, now this I can write in terms of error again, e double dot. Okay, so you remember E is defined here as q minus qd dot. D, okay, Q minus QD. So E double dot and then its derivatives will follow accordingly. Okay, so now this becomes is E dot plus lambda E plus KD times R. Okay, so I can see that this is nothing but R dot. If you see R defined here is in the controller. I want to see that in controller here so that you have a clarity. So R is E dot plus lambda E. Okay, so I can just write here again. R is equal to E dot plus lambda E. So this becomes D times R dot plus now B plus C times R plus KD times R is equal to 0. Okay, and for this we need to propose Lyapunov function. So can you think now for such a kind of a system, if you see what could be, it's not very intuitive because we don't see the derivation of these from the energy perspective here, because we don't have this form that we started off with dq double dot plus all those kind of things. Okay, so it doesn't have directly some energy based connection we can do here right now. Okay, so therefore we can directly kind of go on using like this function candidate v as half. Okay, now I want see when I take a derivative I'll need this d r dot to be substituted, so I'll, and d we know to be inertia matrix, so I can use that d as the inertia matrix here, but instead of now error in terms of e and e dot and other kind of a thing, we can consider this in r terms, and this is r transpose. Okay, is what I consider as energy function. Okay, and this function candidate, if you see in terms of r, if you expand it in terms of error, one can see that both for e and e dot considered as a it will be a quadratic form in e and e dot, and that will be positive definite. Okay, because d is positive definite matrix. Or if you say directly in terms of r, it is you can directly see that this is, because d is positive definite, this has a positive form, and r contains all my system vectors. See, the system has only first order kind of a form here. Okay, so I don't need now r dot to be coming in this v expression at all. If this has been r double dot, then I would need r dot to be coming here for the positive definiteness. Is that part clear? That is what is a important kind of a concept here based on our understanding of positive definite functions. Okay, and we want to propose now this function candidate which is positive definite. Okay, and so now you can work out further from here. Suppose I take a derivative. Okay, v dot. We have now you remember v is equal to r transpose d times r. Okay, and if I take v dot here,
factor of half, right?
Half factor, of course. Yeah, sorry. So half. Now I see, again by using symmetry property I can combine two terms here. Okay, and I'll do that for the other part. I'll first consider r transpose d dot r plus now 2 times, so I will not consider half here. Now R transpose D R dot. Okay, this is what I am considering here, because R dot transpose D R dot, R dot transpose D R is same as R transpose D R dot because of the symmetry of the D matrix. Okay, so that is what property I am using here. Okay, so with that I'll get this D R dot kind of a form here, which was there in my previous equations. If you see, D R dot is coming here. Okay, this is a form. D R dot comes here. Okay, this is what I'll substitute now. Okay, as minus B plus C R minus KDR. Okay, so let me do that here, maybe here. Okay, so that I get more space. So half R transpose now minus B plus C R minus KD R. Okay, so let me erase this. Okay, so plus my term R transpose D dot R will be there. Yeah. Actually, this should
So you
be half.
interchange the
Yeah,
factor of half.
yeah. Half is
First term
here,
won't have.
and first will not have. Okay. So with this, now I can combine the terms the way we want for D dot minus 2C to be coming up. Okay. So R transpose. Okay, and now I use this C term that side, but here only, like, now this is my negative B plus KD and R. Okay, plus now this half R transpose, now this will be D dot minus 2C, this C from the other side, from this side here, this side, and R. Okay, and I know that this is for D dot minus 2C skew symmetry kind of a property, we get this term to be 0. Okay, so this becomes only now minus R transpose B plus C, B plus KD and R. So with B positive and R KD to be chosen to be, B is actually our damping matrix, so it has to be positive. And then KD, some value you choose, positive value for the KD matrix, and then, like, you see that this has a property less than 0. Okay, so see, R vector has both E plus lambda E dot, E dot plus lambda E. So both my E and E dot are going to kind of get represented in R, but they are like some kind of a linear combination. Okay, so so if I now argue from here, like, this argument is important. So by Lyapunov theorem, I can say that with this I can drive this R to go to 0 as t tends to infinity, asymptotic stability for R. Okay, because I have represented system in terms of R only so far. So given a system, the R is equal to 0 equilibrium, if I consider that equilibrium, will have a asymptotic stability based on this proof. Okay, so you can see through the details of the definition of the statement of the theorem, and you can see that this will follow. So R will tend to 0 as t tends to infinity. Now what it means that R tends to 0, R has E dot plus lambda E. Okay, this will tend to 0 as t tends to infinity. Okay, so now if I represent this as E dot, so if this tends to 0, that means E is equal to lambda E dot. Okay, oh sorry, lambda e here. Okay, so E dot is equal to lambda e minus. Okay, and this will be having a, so if lambda is chosen to be a diagonal matrix, positive definite diagonal matrix, then E dot is equal to minus lambda e would lead all the E dots, okay, E1, E2, E3, E4, like that. Okay, we'll have the same form. E1 dot is equal to, say, lambda 1 e minus lambda 1 e and things like that. Okay, and if I now write the solution for each of the elements ei, okay, will be then equal to e to the transpose. Oh, sorry, now this is exponential. Let's let this exponential. Okay, okay, exponential of minus, say now this lambda 1 small lambda for each of these diagonal elements t. Okay, that's the solution of a differential equation. E dot is equal to minus lambda 1 ei dot is equal to lambda. So so this is lambda, I would say lambda I here. Okay, so be lambda I. Okay, so all the errors are then driven to 0. Okay, based on this. So these are the arguments one can use, and then one can say that, okay, so error derivative, so error is driven to 0, and error derivative also is to be will be then driven to 0. Okay, so this will also tend to 0. Okay, one can see from whatever ways, like directly from here also one can see this will follow, or one can say that, okay, if r tends to 0 and e is tending to 0, then e dot also will tend to 0 from this part, definition of r. Okay, so these are kind of arguments one can use, and one can establish this proof that the error indeed asymptotically goes to 0, and this is happening for the case of your controller which has a tracking kind of a nature. This qd dot is coming here, qd dot is not 0. Okay, so qd is in general function of time. Okay, so when the desired trajectory is function of time, you can apply this controller and you can see that the error, so error which is difference between q and qd. Okay, this is error q and qd, the actual trajectory and the desired time varying trajectory. Okay, so this is not a constant part, this is like a time changing term. That error is driven to 0. Okay, so what it means is that, like, your system would if I draw here, just kind of represent, so if this is my trajectory desired, okay, so this is my qd. Okay, then my let me draw this actual trajectory is say originating, say we start at the same point, but or maybe some other point, we don't know where this starting point for the trajectory would be, but this will kind of go and settle down and follow this trajectory exactly. Okay, so this is kind of in the initial transient which will die down, and then it will kind of very perfectly follow this trajectory. That's what it means, that your error is driven to 0 for the tracking trajectory. Okay, so any trajectory that you are given which is smooth function of time, differentiable function of time, your controller is going to follow that trajectory in with very small kind of transients will die down, and then it will completely follow the trajectory very nicely. Okay, and other part, again I'm reiterating that, okay, we see that this controller has this we are these terms which are feed forward terms. Okay, these dA and b plus c times nu. Okay, these are feed forward terms that we are using, and then this is a feedback term. Okay, so this kd and r, this is a feedback term. So feed forward term and feedback term combination we are using here to drive. So that's so this term will take care of most of the the control action to get to this trajectory. and say these transients are initially driven. So these initially you'll find with the transients, this term is going to be contributing more to the control action. Okay, and once the transients die down, like this term also will go down. So so you can afford to use very high gain for this KD part here. When you use high gain for KD, then your trajectory will be maintained along the desired trajectory in a very nice fashion. Okay, so this is how, like, because most of the terms that are there to take care of input needed for the system to be along the trajectory are already fed forward here. Okay, so because of that, the system will anyway going to try to kind of go to that along this trajectory, and whatever small errors coming because of disturbances and other uncertainties in the system, they will be taken care of by this derivative, I mean the feedback part of the term. And that's how, like, you're driven nicely along this trajectory. And now this controller, if you see this, the applicability, it is applicable for all kind of mechanical rigid body systems. Also some kind of a flexible body systems, it is applicable to certain kind of conditions. Okay, so this gives you a very powerful tool for control implementation for any future mechatronic systems. Okay, so that's where, like, we'll stop here. There are other things, like, so say suppose I don't know this D very well. Okay, I have some uncertainty in D, so D is known as D plus delta D. Okay, or B and C are also not known completely. How do I kind of handle that uncertainty part and make the controller robust? There are kind of ways to do that. Basically, the idea there is to kind of, like, keep track of what is my previous torque input, and use that in some way to update things in such a way that I track this I robustly do the tracking. Then one can say, okay, oh, look, I want to adapt to the parameters. Parameters are changing. Okay, then again, like, you can have some certain ways to deal with that kind of situation also. So BC parameters are changing in time slowly. Of course, that change is not as fast as your system bandwidth. I mean, system bandwidth is control is much faster. But if that is changing, then also you can kind of do the other controllers development that is possible. But the base of this all analysis is what we have covered right now. Okay, so as we want to have the small changes of the robustness or adaptiveness, you'll have you'll find some additional terms defined, and some update law for the system parameters can come up in the process of control implementation. So of course, all those things will come as a additional computation cost. Okay, so you see this controller computing will be much costlier than just, like, having the feedback term computed. Okay, in terms of your microcontroller implementation. Okay, so that's how, like, we should think about implementation and theoretical development together in some sense. Or you do the theoretical development and see, okay, what is it really viable for my implementation or not? Those kind of things need to be thought about. So that's how, like, we start making conclusions. So here we have made this conclusion for R alone first. R tends to 0 as T tends to infinity. That is a thing that we are getting by applying Lyapunov asymptotic stability theorem. And now beyond that, we are using some arguments of our own. Okay, these are not arguments from the Lyapunov. So all this from here, whatever we are doing here onwards down, is all like our own kind of arguments, saying that, okay, when R tends to infinity, then E dot plus lambda E tends to infinity. That means, like, E dot will tend to minus lambda E, and based on the solution, one can conclude that each of the components of error, okay, or entire error considered as a vector would proceed to 0 as T tends to infinity. Okay, so that is a kind of idea that we built in here.